Alright, so today we are going to start discussing the basics of statistical thermodynamics. Before I get anywhere, I need to lay a disclaimer. I too am a student, so I'm going to explain this as best as I have understood it, but I could be wrong. Um, but I'll be doing my best. That's one. And then the reference for the discussion that we are having today is primarily from Julia Nicola Atkins, chapter 15. So today we are going to work on the most basic stuff of statistical thermodynamics. Why bother with this in the first place? The principle of counting and then the statistical weight, and uh, the basis of the Boltzmann equation, and we'll be introducing that as well. And then we'll also talk about the partition function as well as what is beta. So let's get on with it. So the principle of counting is something that is fundamentally important when you're trying to discuss statistical thermodynamics. Principle of counting. Right. So the idea behind the principle of counting is that if you have a process uh, which has several steps, right? Step one, step two, right, and then step three. The number of ways in which this process can be done is equal to the number of ways in which step x1 can be done multiplied by the number of ways in which step 2 can be done multiplied by the number of ways in which step 3 can be done, right? This is basically the principle of counting. So if we from this basis we arrive at two equations, NPR and NCR, right? So how do we go from here to here? That's mathematics, and that's for another discussion altogether. But what we need to know is that the NPR formula is used when you have n number of items, right, to be arranged. It's important that we understand the word arrange, because when you arrange things, the order matters, right? In a length, in, let's say, in R spots, right? Whereas you use the NCR formula, which is this one, right? I'm going to rewrite this in a different color so that you could, right? So this is the NPR formula. This is where I use the NPR. Whereas in the case of when you are arranging n items to be grouped, right? So this is grouping. Grouping is different from arranging, right? When you group things together, the order doesn't matter, right? In R spots, right? In R spots. Okay. So here we use the NPR formula. We use the NPR formula, and in this case we use the NCR formula, right? So this is the basis. This is the important factors that we need to note when you are considering arranging and grouping. So the equation, the expanded forms of this is like notation. So if you write it in the expanded form, what we have is n factorial divided by r factorial into n minus r factorial. In this case, we have n factorial divided by n minus r factorial, right? So these two equations we will be using in the first part of our discussion a little bit, so that we know how to do, we practice how to do counting of different states, right? So let us consider distributing. Let us think about the fact, right? So before before I go on to the next step, I missed the first topic, which is why bother with this, right? Why bother with statistical thermodynamics in the first place? Uh, right? So why? What's the point? So when you think about what we know about molecules and different particles, we have the ability to figure out different properties of individual particles, right? Using spectroscopy or various forms of spectroscopy, we can figure out the moment of inertia, the energy, the translational motion, and between quantum mechanics and spectroscopy, we know about individual particles, right? So that is mainly from spectroscopy, and maybe you could use quantum mechanics and uh, various other various other techniques, right? So you could tell a lot about the individual particles as well as the individual energy levels and all of that. So about the molecules itself, you could get a lot of idea using these set of techniques, right? At the same time, we have another area of study, thermodynamics, right? Thermodynamics, we've been repeatedly told whenever we study thermodynamics is that thermodynamics is to do with bulk properties, right? So when you have a lot of molecules together in the bulk, that is where the concept of thermodynamics applies. Um, so thermodynamic quantities like entropy or uh, Gibbs free energy or temperature, all of these apply only on the bulk. So now there's a question: how can we connect our understanding of individual molecules and their behavior to our understanding of the behavior of the bulk? There has to be a connection, right? Because these guys make up a bulk, so there has to be a connection. And what is that connection? That connection is discovered or studied by means of statistical thermodynamics, right? That's the point. The objective is to make this connection, right? So now the argument that our discussion follows is uh, from spectroscopy and quantum mechanics. We for example, we know, let us consider translation. We want to figure out the average translational motion, let's say, right, of these molecules. Between these techniques, we can figure out the difference of different energy levels, right? What are the different energy levels and what is going to be the velocity in these different energy levels, and all of that could be, right, determined. Well, let's not necessarily specify to that range, but the point is that the behavior at different energy levels or the quantities or the values associated with its presence in different energy levels can be determined, right? If it is in the first energy level, it will be like this. It will be in the second energy level, it will be in such condition, right? If it's in third energy level, it's in such condition. So this information we can determine from spectroscopy. So from here, uh, if we can tell how many molecules are in what states, right? Or what fraction of our particles in our system is in what states, then we could get the average of it, right? Because we know the individual energies or individual quantities. So if we could determine how much of what energy level is available, we could determine the thermodynamics. We could connect it to thermodynamics. That's the idea. So the connector is figuring out the distribution, right? The distribution of these different energy levels. How much of these particles are in this level, how much of them are in this level, and likewise the distribution. So that is where it becomes important. The principle of counting comes in, right? Because what we are going to do is essentially we are going to count the number of particles in the first energy level, count the number of particles in the second energy level, count them, and then multiply them by these different values to get the average, right? So that is the general approach we are going to take. So let's think about, right. I'm not going to get very specific, right. Let's say we know that our system. Let's imagine a system with, let's say, 10 particles or 3 particles. So I'm going to erase this part, right. So I'm going to continue with the principles of counting. right? So let's imagine a system with 10 particles, right? Uh, okay. Let's say there are three particles, right? And now we know that energy is quantized. Now, let's say that there are 4 units of energy, right? There are 4 units of energy. Now, because we know, let's imagine that we know the energies of the different. Now, let's say this particle has different energy levels, um, E1, right? E2, E3, and likewise, right? And there can only be 1 unit of energy in each energy level for a given particle. So these are the facts that we know about it, right? There can only be one particle, right? Let's say one unit of energy. One particle can have only 1 unit of energy in a energy level, right? In a given energy level. There are multiple energy levels continuing like this, and we want to see the distribution of the different energy of the different particles, right? So you have 4 units of energy. Let's agree on notation, right? This, let's say we're going to say we have three particles, right? Um, we have three particles, 4 units of energy. How can we put them? How can we put these 4 units of energy into these three particles? Now we can put all 4 units of energy into one particle, right? And put no energy into the other two particles, right? We can put 3 and 1, right? You can put 2 and 1 and 1. You can put 2 and 2, and these are ways of distributing the various units of energy, right? Um, so if we will agree on a way of writing what we have here, right? So this is particle 1, this is particle 2, this is particle 3. We have 4 particles. We have particle 1 with all four energy units, right? And then you have particle 1 with 3 energy units, and particle 2 with 1 energy unit, particle 1 with 2 energy units, particle 2 with 1 energy unit, and likewise, right? So we could write this like this, right? If we consider our system, in our system, in the first energy level there is only one particle, in the second energy level there is another particle, right? In the third energy level as well there's another particle, and then, but bit of a correction there. In this situation, right? Um, all of there are no particles in the first energy level, right? There are none of them are there in the first energy level. In the second energy level, there is none. In the third energy level, there is none. There is one particle in the fourth energy level. But also, there are two particles in the zeroth energy level, right? So, two particles in the zeroth energy level, one particle in the fourth energy level, right? And then in the fifth energy level, there is none, sixth, and likewise, right? So, this is the number of particles in the zeroth energy level, number of particles in the first energy level, number of particles in the second energy level, number of particles in the third energy level, number of particles in the fourth energy level, and likewise. Right? This is our way of describing this configuration. For this configuration, we are going to have in the zeroth energy level, there is one particle. In the first energy level, there is one particle. In the second energy level, there is nothing, right? And there is one particle in the third energy level, and then the rest of them are zero, right? If you consider this situation, in the second energy level, in the zeroth energy level, there are no particles, right? There's nobody with zero energy. There are two particles with one energy, and there are one particle in the second energy level, and the rest of them is zero. In the final one, we can write this configuration as zero particles in the zeroth energy level, zero in the first energy, two in the second energy. Sorry, there's one on the zeroth energy level, right? This one is on the zeroth energy level, so there is one, and then two on the second, and the rest of it is zero. Okay, So these are different ways of describing our two different ways of describing the same thing, right? So we talked about how the energies particles are distributed in different particles over here, whereas in here we are describing the configuration, right? How many particles in each energy level. All right. So now to do the counting, so I'm going to erase these two formulas so that I can do the counting, right? If we consider this, we'll give them names, right? We'll give this, consider this to be the energy level configuration 1, configuration 2, configuration 3, and configuration 4. Four different ways of distributing these 4 units of energy um, in 3 particles, right? Now, if we consider the ways in which this can be achieved, right? uh, I've named this as particle 1, particle 2, particle 3, right? So you can easily see that this configuration can be achieved in 3 different ways, right? Uh, if you think about it, right? So you can have all 4 of these energy, right? It could be, let me, right? Could be that particle 1 has all 4 units of energy and particle 2 doesn't have any energy, particle 3 has no energy. Alternately, it could be that particle 1 has no energy, particle 2 has 4 units of energy, and particle 3 continues to have no energy. Or it could be that particle 4 has particle 3 has all 4 units of energy, and the other two have nothing, right? Right. So all 3 of these belong to configuration 1, right? So if you try to describe this using the using the principle of counting, right? So you basically have a one slot here, right? You have one slot over there, 2 slots over there, right? You have in the 0th energy level, you have 2 slots. In the 4th energy level, you have 1 slot, right? And you have 3 particles. So how can you group 3 particles into this second energy level? It's 3C2, right? We have 3 particles and you are going to group them into the 0th energy level as 2 particles. So it's 3C2, right? And once you put 2 there, there is 1 remaining. That's going to be 1C1. So 1C1 is 1. 3C2 is, if you do the simplification, you get 3, right? You get 3. 3 factorial. Okay. Okay. So it's going to be 3 factorial divided by 2 factorial, 1 factorial, right? So that is 3 because these two will cancel off, and then this is going to be 1. So there's only one way, 3 ways, as we have identified earlier. By just logic, we can see it's 3. By mathematical treatment, we have also realized that there are only 3 ways, 3 multiplied by 1 number of ways of getting this configuration, right? If we continue the same kind of treatment for the second configuration, right? This is for the first configuration. For the second configuration, there are, let's look at this, right? Second configuration, there are 3 different points, right? So you have 3 particles which could be placed in this group, right? In this position, in the 0th position. And, right, the second step is we could place 2 of the remaining particles in this location, or you could place 1 of the remaining particle in the 1 location, right? So 3C1 is 3, right? It's 3 factorial. It's 3 factorial over 2 factorial, 1 factorial, right? And then it's now if we were to do this in a very perfect way, considering everything, right? How it should go is we consider there's one vacancy here. There are three particles which could be placed. So 3C1. Again, there's one vacancy, two particles to be placed, but there is zero vacancies here. So although there is one particle, there are zero vacancies, and one particle, one vacancy, right? Zero particles, zero vacancies, right? This will continue until you cover all of the different energy levels available. So if you write this down, 3C1 is 3, 2C1 is 2. If you do the simplification, you will get that value. 1C0 is 1, 1C1 is also 1, everything else is 0, C0 is 1, right? Because ways of combining no particles in no basis, there's only one way you cannot combine no particles, right? It's just if you substitute 0 into this formula, you get 1, right? So there are 6 ways of achieving the second configuration. If you consider this configuration, configuration number 3, I'll write it in a different color so that it's easy to see, right? This configuration, right? It's 3 factor 3. So let's say there is zero vacancies, but there are 3 particles. So 3C0, right? There are again 3 particles, right? 2 vacancies, and then 3. You have already placed 2 particles, so you're left with 1 particle, 1 vacancy, and then it would continue, right? If you write it, expand this 3 factorial over 0 factorial into 3 factorial, right? Multiplied by 3 factorial into 2 factorial into 1 factorial. Multiplied by 1 factorial into 1 factorial into 1 factorial. But this is the very proper way of doing it. This expanded way of doing it is the very proper way of doing it. But if you are asked to just place 4 units on 3 particles, we can simply go take this path, right? I'll do the last question in the short path so that we get the point. So these, why I have written this expanded form, so we can continue to the next part of our discussion about statistical weights and how the statistical weight formula is derived, right? With the objective of connecting to that, I've written the expanded forms, but the shortened form, that's the easier way to go about it. Anyways, 3 factorial or 2 factorial, that becomes 3. This becomes 1. This becomes 1, and likewise. So you're left with 3 over here. All right. And then finally, we'll go for this one, right? The fourth configuration. We don't have to worry about the zeros here. So the quicker way of doing it, there's one vacancy, there are 3 particles, right? So 3C 1. 0 vacancies, we'll not bother because we know it's going to return 1. 2 vacancies, 3 particles. We've already placed 1 there, right? So 2 remaining, 2 vacancies, 2 particles, right? So 3C1 is 3, 2C2 is 1, right? You get 3. So there are 15 different ways in which you could distribute 4 units of energy, assuming there is assuming that the ground state of at least one particle is filled, right? So this is just 15 different ways of distributing 4 units of energy. So there are 15 different ways, right? Out of those, 6 belong to the configuration number 2. 1 are configuration number 3, 3 are configuration number 3, 4 are configuration number 3. So if you want to talk about the probability, right, if you randomly just throw all of these 4 particles, and you randomly just throw all of these 4 particles into these 3 different uh, all of these 4 energy units into these 3 particles, for quantas is the technical term. So you distribute all 4 units into 3 particles, and they can take 1 out of 15 forms, right? So since it's random, any one of those 15 is equally likely, right? So if you want to talk about probability of it achieving this configuration 1, right? So there are 3 ways in which configuration 1 can be achieved out of 15 different possibilities, right? So the probability of configuration 1 coming is 3 over 15. Same way, you finding the system in configuration 2 is 6 out of 15 different ways, right? Probability of you finding it in configuration 3 is 3 out of 15 different ways, and probability of finding it in configuration 4 is also 3 out of 15 different ways, right? So you could see that configuration 2 is twice as likely as anything else, right? So that is an important observation that we have here. And we need to understand we have a very small number of particles and a small amount of energy. This difference, clearly there's one system that is more dominant than the other configurations, right? If you randomly look at your system, you're twice as likely to find this one than you are likely to find others, right? So but this domination effect is more intensified when you have a larger number of particles and larger number of energies. So we'll move on to the statistical weight. So this is right. This 3 over 5, 6 over 15, 3 over 15, 6 over 15. These are probabilities, right? How likely are you going to find each configuration? That is related to the statistical weight, right? It is related to how likely you are going to find a particular configuration. So the statistical weight equation will move on. I'm going to erase this distribution discussion, and then we are going to move on to the discussion on statistical weights. All right, so you have the weight equation, right? So we have determined the statistical weights here: 3, 6, 3, and 3, right? So you can see that this is derived by considering you have total number of particles NC n placed on the number of you know what, I'll not go into the mathematical complication behind the statistical weight formula. We'll just right away get to the formula itself, right? So this is the statistical weight formula. This is basically the number of ways in which you are going to achieve a particular configuration, right? So n factorial over n1 is the number of particles in the first energy level, n2 is the number of particles in the second energy level, n3 is the number of particles in the third energy level, and likewise, right? So let's do this equation for each of these different configurations, right? So in this one, um, there were let's say for the first one, right, I'm going to write it right on top of this, right? So anyways there were always three particles, right? So in the zeroth energy level there were no particles, first energy level there were no particles, um, third energy level there were no particles, fourth energy level there was one particle, right? So you get 3 factorial over 1 factorial, which is 6. All right, so in the zeroth energy level there were two particles, right? So you get 3 here. For this situation, we had three particles anyways, right? In the zeroth energy level, we had one particle, right? In the second energy level, we had, in the first energy level, we had one particle, and in the second energy level, we had no particles. In the third energy level, we had one particle, right? So this, and then in the remaining energy levels you had nothing, right? 6. This one you had anyways 3 particles in total, that doesn't change. You had um, 0 particles, sorry, you had 0 particles in the 0th energy level, 1 particle in the first energy level, 1 particle in the 2 particles in the second energy level, and 1 particle in the third energy level, and likewise you had 2 particles in the first energy level and 1 particle in the second energy level, right? This was the configuration. This was the distribution, right? 2 to 1. So 2 particles, 2 1 1, right? This was the distribution. 2 particles in the second energy level, 1 particle, 2 particles in the first energy level, 1 particle in the second energy level, right? So that was the distribution that we had over there. and we get, write this a little more clearly, right? So zero particles in the zeroth energy level, two particles in the first energy level, one particle in the first energy level, and likewise you get three. Here you have 3 factorial. It's going to be as it is. Here the distribution was 2 to 0, right? So one particle in the zeroth energy level, this one, no particles in the first energy level, two of these in the second energy level, and likewise, which is also 3. So this equation gives us the statistical weight. You arrive at this equation by simplifying this one. You expand this and simplify it, you arrive at this equation. That is in order to demonstrate the connection and relevancy of this statistical formula equation, statistical weight equation, is why we wrote it in this expanded form. You could easily use this equation and then get this directly. All right. So, okay. Now you can see that so we're going to move into the next part, right? Introducing the Boltzmann equation and the basis of it. Right? So the basis of the Boltzmann equation is that, uh, before we get there, right? So let's say you could see that one configuration is more likely than others, right? Now, if we think about, I'm going to erase all of this, right? And we'll look at a different system with much more particles and much more energy, right? So we'll forget about the energy limitation and just think about a configuration where there is, let's say, 100 particles, right, in the zeroth energy level and none in the higher energy level. So the weight of this system, weight of this configuration, can be written as 100 factorial divided by 100 factorial, because the zeroth energy level, and then 0 in the next, 0 in the next. So this is 1, right? 100 factorials cancel off with each other. But if you consider that two of these particles are on a higher energy level, so there is 98 here, and then 2 here, and then 0, and then in the zeroth energy level, there's 98 particles. You moved 2 to a slightly higher energy level, to the first energy level. If you determine the statistical weight of this one, it's 98 factorial divided by, right? Sorry, it's 100 because you have 100 particles. Capital N is 100. 100 factorial. We have 98 factorial over there, right? And then 2 factorial in the next energy level, and then 0 factorial, and it continues, right? If you simplify this, you arrive at 99 multiplied by 50, right? You can see that if this system can only have these two, let's imagine for some reason that the system is restricted to only these two possible configurations, you can clearly see that this one is going to be found much more often than this one, right? If you randomly look at your system, you'll almost always find this configuration, right? Because it's what, this is nearly 500, right? Almost 500. I think it's 495, right? So it's 1 is to 500. So if you look at it 500, if you look at it 500 times, almost 499 times you will see this configuration and not that one. And what that means is, in this example where only these two configurations, you have 100 particles and all of them being either in the basic, in the zeroth energy level, or only two of them being in the next energy level. If these are the only two possible configurations of our system, this configuration is what you are going to find nearly all the time, right? This connects back to the discussion that I had at the beginning of this discussion, and as to why we do this statistical treatment, right? Now we can tell in this imaginary system, right? That um, we can tell clearly that this configuration is what is going to be present in our system. Therefore, you could, let's say, this one, if this one has, if the zeroth energy level has, hypothetically, let's say 10 kilojoules of energy for whatever function, and this one has 20 kilojoules of energy for whatever function, right? It's just an imaginary energy associated with that state, right? We can say that the total energy of this system is probably going to be 98 into 10 plus 20 into 2 divided by 100, right? This is the average energy of the system, right? Let's say energy average, right? Of the system is going to be this. So by understanding what configuration is going to be the most present in our system, we can determine various bulk quantities, right? So what this means is if you look at your system, you will find this value, although you will find this observation, whatever output of this calculation, that's what you're going to see if you look at the system. In practice, uh, these values, right, of associated with individual energy levels, those can be determined using either quantum or calculations, or majorly using spectroscopic techniques, right? Okay, so now this begs the question, this is an imaginary system, right? In real systems, what configuration dominates the system, right? We can see like one system is going to overwhelmingly dominate our practical systems. Although it's possible for energy for particles to have, for example, any a range of different rotational energy levels, right? One particular configuration is going to dominate the system that we're going to see. And what is that configuration? That is the question that the Boltzmann distribution answers, right? So we go from this, right? Essentially, the question we're trying to answer is at what distribution, at what values of n1, n2, n3, n5, n6, and all the way up to n infinity, at what combination of these values will W maximize, right? When will W become maximum? And whenever W becomes maximum, that is when, that is the configuration, right? Whatever configuration that has the highest W, and that has the associated distribution of these n1, n2, n3 values. That would be the distribution that would dominate. So we are trying to find the maximum, uh, right? So the question is, for what values of n1, n2, and likewise up to n, right? The number of particles in, let's also include a zeroth energy level. Number of particles in the zeroth energy level, number of particles in the first energy level, number of particles of second energy level. So what values of these number of particles in different energy levels will W become max, be the maximum, right? So now, because these factorials are a little difficult for us to treat mathematically, they're difficult to work with. Because of that, we introduce the Stirling approximation. As chemists, we want our calculations to reflect the reality as best as possible, and we are comfortable with approximations as long as it gives reliable values, right? So we are going to use something called the Stirling approximation, right? So the Stirling approximation is a mathematical technique, right, which basically means, says that ln n factorial is equal to n ln n minus n, right? So now, because we have the factorial associated with ln and linear logarithmic and linear values, right? These are functions which maths works with quite easily. So because of this reason, instead of finding when W will be maximum, we find when ln W will be maximum, right? So when does LNW become maximum for any kind of formula, right? For any kind of situation, let's say for whatever y to be maximum, to find the maximum point of y, uh, right? To find the maximum point of y, we just take dy and then equate it to 0. Similar manner, we take d ln w and then equate it to 0, right? Um, Now, in our real system, there are two restrictions that we need to think about. So, we are going to think about the fact that our total energy has to be conserved. That's actually the truth, no? So whatever different configurations we have, all of those different configurations should have the same energy. In the previous example that we discussed, we had 4 different configurations, and all 4 of those different configurations always had 4 units of energy. So that energy is restricted. It is equal to the number of particles in each energy level multiplied the energy of the total energy level, right? This is one restriction. The other one is the total number of particles. That is also restricted, right? So you use these 2 restrictions and then also a mathematical procedure known as the method of undetermined multipliers, right? That is where you get the Lagrangian function and all of that. Method of undetermined multipliers. So you use um, various techniques, right? And then you determine the you treat these 3 restrictions, right? So you have an equation here, right? You can use this equation. So this essentially you can write it like this, right? Okay, so there are many different ways of writing this equation, and you do an entire mathematical treatment. That is not something that we are going to discuss in this video, right? We are going to move on to the final output of this entire treatment. The final output is the Boltzmann equation, right? So let me erase all of this and then arrive at the Boltzmann equation. So this is the basis of the Boltzmann equation. We are trying to maximize, right? So we try to maximize W, right? When does the statistical weight maximize, right? When energy is conserved and number of particles is fixed, right? This is basically what we do, right? When we do this, you arrive at an equation which is this. We find ultimately we find the distribution, right, where W is maximum, right? And in that distribution which dominates our system, where W is maximum, is called the Boltzmann distribution, right? Boltzmann distribution. So if you, although many different configurations are possible, uh, for a system that is in practice, right, because of the effect that we discussed earlier, right? If a system can be achieved in more different ways, it's more likely to be found. Simply because of that fact, as well as these 2 restrictions, if you look at your system, you will almost always find a specific configuration present, right? Like that single configuration would describe the entire system in general, right? And that configuration is called the Boltzmann distribution. So in the Boltzmann distribution, if you have a number of particles, right, n1, there'll be a certain number of n1 particles, there'll be a certain number of particles in the second energy level, and a certain number of particles in n3 energy levels, and likewise, right? So the Boltzmann distribution is expressed in this form. Ni, the number of particles in a given energy level, right, divided by the total number of particles is equal to exponent of minus beta to the power energy of that particular energy level, right, divided by Q. You can see that this is essentially a probability, right? So this can also be mentioned as probability of finding a particle at the ith energy level as this, right? So probability of finding a particle at the, if you look at your system, the chances of you finding a particle at the ith energy level, or the, let's say there are, let's say you are going to look at the system and then you pick a particle, and the chances of it being in the third energy level, for example, can be written as e to the power minus b E3, energy of the third energy level, divided by q. Q is the partition function, right? So partition function is basically sum of this value for all of the different energy levels. So summation of e to the power minus beta ei I from 1 to n, right? Whatever number of energy levels there are available, right? So this is your Boltzmann equation. This is a very important equation that is used in many different applications, because it allows us to connect our knowledge of individual energy levels to the overall system. Yeah, so these EI values, those are determined using spectroscopic techniques or various other calculations. And as soon as we know these EI values for a series of different energy levels, we can connect it to the number of particles which are going to be present in our system and then predict the bulk behavior of our system, right? So this is the partition coefficient, right? So there are two question marks in this equation, right? Two question marks, two things that we have kind of question about. One is what is Q, and the other one is what is beta, right? So we'll discuss what is Q first, and then we'll go on to what is beta. All right. Okay. Right. So we can apply a small modification in this equation, right? Because there can be different energy levels, let's say, right, or energy locations which have the same energy, which are degenerate, right? So you could have um, particles at the ith energy level, and there can be ith energy level can have, let's say, g number of degenerate positions. In that case, gi minus bei is used. This g is added to avoid um, overcounting, right, or undercounting, right, to get the counting right use, because if there are many different degenerate levels present at the same energy level, then it has to be multiplied. And in that light, the partition function becomes summation of gi exponent of minus beta ei, right? Okay, so this is the equation that we are going to work with. This is the Boltzmann equation, that is the one that is used in general, right? Okay, so we'll look at a bunch of situations and then try to understand what this Q is, right? What is this Q and how does it relate to physical systems, and what can we understand by looking at Q? Okay, so beta. We'll try to understand what is beta, right? What is beta? Okay, so what is beta? Beta, to understand that, we are going to visit one of the most celebrated postulates in this area, that is the Boltzmann's postulate. The idea is this: if you think about the entropy, entropy is chaos, is about how randomness, right? How many different ways can a system have, right? The more random a system, the higher the entropy. That's the idea, right? Same, if you really think about it, L and W, right? L and W, or rather W, right? Statistical weight is also, here's a direct relationship, because the more ways a system can be found, the more random it is, right? The more ways in which we can create a same system, a same configuration, the more random it is. So based on that, there is a equation called the Boltzmann equation. This is a postulate, right? There's a good justification for this, but that is beyond the scope of this video. So this is the Boltzmann equation, and we're going to start from this and try to find out what is beta. um, we are going to approach this in two different sides, right? To double, like a double-edged approach. That's what we are going to do now. So we are going to start from this side of the equation, right? So let us consider d, L, and W, right? So we know by the equation of statistical weight, right? Because statistical weight is equal to n factorial divided by n1 factorial n2 factorial and likewise, right? So we can say this is d ln n factorial, right, minus ln n1 factorial minus ln n2 factorial and likewise, right? Because we're talking about change, right, differential. If the total number of particles in our system is fixed, this is going to go to zero, right? So you have this part becomes zero, and you have then let's say minus, these parts are going to be left, right? We're going to write it as a summation ln ni factorial, right, where I goes from 1 and upwards. Using the Stirling's approximation, we can write it as ni ln ni ni minus ni, right? Differential. We need to have that differential term here that can't disappear, right? Uh, differential, right? Okay, so this is the summation. We need to understand the sum is over the entire range. Now you can distribute that sum, that is the behavior, that is the property of sigma. I goes from ni ln ni, right? The minus has to be there in front, so we keep the minus right there. Minus multiply, we'll put it as plus, right? ln, we have to keep the differential again. I keep using that. So let's differential, right? ni. Um, Sum of differential is equal to differential of sum, right? This is basically dn, sum of ni is capital N, right? This is not a variable, it doesn't change, capital N is fixed. Therefore, this also goes to 0, right? So now you are left with just this summation of I d ni ln ni, right? Now we bring in the Boltzmann equation, right? So let's say you have for the zeroth energy level, right, n naught, you can say, let's say n naught over n, for example, right? Let's say using the Boltzmann equation, we can write e to the power minus beta e naught divided by, I'm just gonna write q as the, because the partition function, right? For ni, we can say ni over n equals e to the power minus beta ei over q, right? Now you can divide this one by this one, right? Divide those two equations, and then you can get another equation like this, right? Um, Basically, ni over n naught is equal to e to the power minus beta ei minus e naught, right? Now, normally when we are doing these calculations, we assume that the 0 point energy is negligible or not negligible. We consider it to be zero. We start measuring from the 0 point, or rather from the zeroth energy level, right? So this can be written as e to the power minus beta ei, right? So this is possible to write it in this way. Okay. Okay. So let us erase the parts at the top. right? So we arrived at this equation. This one can be written as, right, ln ni minus ln n naught is equal to minus beta ei. You write it like this, right? So once you have written it that way, you could move this one to this side like this, ln n naught, right? And then substitute this whole thing over there instead of ln ni, right? So now you have d, this is equal to d ln w, right? ln w is equal to sum, right, of ni minus beta ei plus ln n naught, right? Uh, right. So we could then write this again. I forgot to include the d part, differential of this whole thing, right? So this could then be written as d, right, beta ei all right. So we could write this as, right, we'll keep the summation as it is, d ni, take the minus in front. Oh, two minuses will cancel out, right? So beta ei. And then again we'll keep the summation as it is. The minus minus would, we should have a minus will come over here. Summation is going to be d ni ln n naught, right? Again, beta is a constant. Take beta out, right? Summation of, right? You can take earlier I told you summation of differential is differential of summation, right? In general, right? So you could use that understanding and write it ei ni, right? So you would write this way, and this could be written. This is a constant, right? With respect to, right? You could write ln n naught. You could take it out because it doesn't change with I, right? With respect to I, this is constant, right? So summation, you can take the differential also out, the sum of n, right? You can see this is just capital N, right? This is simply capital N, right? So this is change in the total number of particles, which is 0, right? Because of that, this term goes to 0. Okay. All right. So we are only left with this term, which means our d ln w is equal to, this is basically ei ni is energy, right? If you consider this whole term, and you consider this ei ni, the product is energy at the ith level, right? So this whole thing is basically total energy, as you might be able to notice, right? So this is dE, beta dE, right? ln w is equal to beta dE. And this is an important observation right here. So we got this from statistical thermodynamics, right? From statistical treatment of our basic understandings. Now we get on to from the actual thermodynamics, right? From normal thermodynamics, we know that S is equal to Q over T, right? So ds is dq over dt, right? Now, if you think about dq, right, that is basically change in energy in the system, because using our first law of thermodynamics, delta U, let me say du is equal to dq plus d w, right? Assuming that there is no mechanical work, du equals dq, and du and de is basically the same concept, right? These two are essentially the same concept, right? So let's bear that in mind, and then we'll move on to the next step, right? Erase this part. uh, because this is energy, and here when we say a total energy, internal energy, it's pretty much the same thing in the context that we are working right now. Okay, so ds, now we had an equation earlier, right? The Boltzmann equation, S equals k ln w, right? So ds is equal to Boltzmann constant is a constant, right? So we leave the constant out, d ln w, and we write this one over here, beta de. Instead of ln w, we leave k as it is, and we write this one, because dq, as we can see here, is du, which is also de. We can write de over t, right? So basically, this one combining with these two, we can write it like this, right? So as you can see, the de cancels off, right? Cancels off. You're left with beta is equal to 1 over k, right? So we started off with the Boltzmann's postulate and the Boltzmann equation, and then we arrived at the meaning of beta, right? Beta is 1 over kt. So that is also complete. So one last topic for the day remaining: what is the partition function? And with that, we will have a thorough understanding of the overall picture of statistical thermodynamics, because everything else on statistical thermodynamics is built on top of the equation, the Boltzmann distribution. So what is Q? That's the wrong Q, right? Simple Q. What is this, right? So we now understand that beta is equal to 1 over kt. So what is Q? What does it mean? And what can we understand from that number or from that formula or equation, right? So when we earlier discussed, because different one energy level can have different vacancies, or different energy levels can be degenerate, right? We can write Q as summation of gi exponent of minus beta ei. This equation is what we are going to work with, right? Um, okay. So let us imagine a system where t goes to infinity, right? Let t goes to 0, let's say, right? So when t goes to 0, beta goes to infinity, right? Beta goes to infinity. So when beta goes to infinity, e to the power minus beta ei goes to 0, right? What does this mean is, right? So now that observation is there. Now, like I earlier mentioned, when you are working with these systems, we usually say E naught, zeroth energy level, has zero energy, right? Because we are measuring energy from the zero energy level. So when you consider the expansion of this term, right, you can see that Q is equal to, let's say, G0 e to the power minus beta E0, right, plus G1 plus e to the power minus beta E1, and likewise, right? So why I'm not plus, multiply, right? So we will not mention that at all. Okay, so the reason why I don't continue this series is because it doesn't matter when you go forward, right? Because E naught is 0, this term becomes 0, right? This particular exponent is 0. In that case, this whole thing becomes 1, right? So in here, from G1 and above, EI is not 0, right? Because of that, and because beta is going to infinity, this goes to 0, right? So basically Q equals G naught, right? So what does this mean, right? In a very physical terms, is when temperature becomes 0, partition function is equal to the degeneracy of the zeroth energy level, right? Uh, think about it, right? When temperature is 0, there's virtually no energy, right? Uh, and the partition function is equal to the number of degenerate levels at the most ground state. That's what this is. Now we'll look at t. What happens when t goes to infinity, right? When t goes to infinity, beta goes to 0, right? Uh, when beta goes to 0, if you consider the expansion of this part, right? Q is equal to gi. So let's say g0 e to the power. This is 0, not so e to the power 0, right? And then g1, right? You can see that this trend is going to continue, right? Because beta is 0 everywhere, right? And that means Q is equal to the sum of Gi, all right? So when the temperature is infinitely high, Q is equal to the sum of all of the energy levels available, all of the degenerate energy levels available all the way up to infinity. So can you see that? Q is telling us what are the energy levels our system can access at a given temperature, right? When the temperature is 0, our system obviously there is no energy, therefore it can't go to higher energy levels. So it can only access the lowest energy level, right? So only G naught is available for the system to access when the temperature is 0, right? When the temperature is infinite, then all of the energy levels become accessible, right? So in other words, Q is telling us what are the energy levels that our system can access, the accessible set of energy levels. That is what Q is telling us. All right, so with that, we have covered the content that we wanted to cover for the day. Once again, repeating the disclaimer that I mentioned at the beginning of the video, this is the best explanation that I could give based on what I understood. Um, could be mistakes, there could be errors, but this is the best that we have in terms of what I have understood. So to recap everything that we looked at today, it's a very short summary, right? So you have the principle of counting, right? So you could count the number of energy levels. So first of all, we talked about why we uh, study the statistical thermodynamics in the first place. We want to use our understanding of from spectroscopy about individual particles and then connect it to the bulk behavior, which is thermodynamics, right? That is the reason why we study this in the first place, right? To do this, to make this connection, right? And the next topic that we looked at was the uh, principle of counting, and from the principle of counting we got this equation which describes the statistical weight of a particular configuration, where n is the total number of particles and n1 is the number of particles in the first energy level, n0 is the number of particles in the zeroth energy level, n2 is the number of particles in the second energy level, and likewise. And from this, as well as the two restrictions, right, total energy is restrained and then the total number of particles is restrained. From that understanding, we arrived at the Boltzmann equation, right? The Boltzmann equation is basically the probability of finding particle I, um, particle the probability of finding a particle at the ith energy level, which can also be expressed like this: number of particles in ith energy level, total number of particles equal to natural exponent of E minus beta e to the power I divided by Q, right? And we discussed a little bit on the mathematical treatment behind this, but there's a lot of math that goes between this, right? And then also the two restrict. I'll write the restrictions down because they are important, right? Ni equals N E equals EI N, right? Uh, these two restrictions, the combination of these three is how you get to here, right? And one thing that we observed when we discussed the statistical weight is that one system tends to dominate our system, right? One configuration tends to dominate our system, and that dominant configuration is called the Boltzmann, the dominant configurations distribution. The way this N1, N0, N2, N3 is distributed in that dominant configuration is called the Boltzmann distribution, and this equation describes the Boltzmann distribution. And it can be expressed like this: Q means this. Q can be written like this. Wait, we'll add the degeneracy as well to this one. It's a more general equation. Uh, okay, so Q is equal to G summation of Gi E minus beta Ei divided by, okay, there's no division there. All right. Okay. Right. Okay. So finally, we have the meaning of beta, right? We discussed how this tells us the number of energy levels that is accessible for a given temperature, right? What are the energy levels that our system can possibly access at a given temperature, right? Finally, we started from the Boltzmann equation, K, L, and W, and then we arrived at the meaning of beta, which is 1 over KT, right? So this discussion about the meaning of beta, there are many different ways to arrive at it. Atkins uses a different way. It uses the internal energy. I personally don't like that approach because it uses thermodynamics. Because the whole point of this entire discussion is to go from our understanding of individual particles, we mathematically treat it, and then we find a connection to thermodynamic bulk behavior. So to use a thermodynamic value, a thermodynamic equation, which is internal energy, you have thermodynamics equations or internal various equations, right? So those equations are used to determine beta, and that's like a cyclic reference, right? We're trying to go from here to here using from that side. It's not wrong per se, but I prefer this approach more. And so that's it for today's discussion.